11.1, one more example. It's example 7. The nth order Taylor polynomial for f of x equals natural log of 1 minus x centered at x equals 0 is p sub n of x equals negative summation. Okay, they're giving me this information. This would be x to the k over k, which if they wrote out terms of negative x, then negative x squared over 2, then negative x cubed over 3, negative dot dot dot, out to negative x to the n over n. What's the maximum error in approximating it by p sub 3 of x for values in the interval negative 1/2 to 1/2? Okay, so I need the remainder. R sub 3 is going to be the fourth term. So it's going to be this. And c is between 0 and x. Computing that derivative, okay, we have to go all the way down and get to the fourth derivative. Nice. And they just told us what that was, but we'll go ahead and do it. F prime of x is going to be negative 1 over 1 minus x. F double prime is going to be positive, and then negative again, 1 over 1 minus x squared. The third derivative is then going to be positive 2, negative 2, 1 minus x to the negative 3. And the fourth derivative would be positive 6, but negative 1 minus x to the negative 4. Oh, I forgot the 6. There we go. So if you look at that derivative on the interval negative 1/2 to 1/2, the biggest error would actually, they're going to be, yes, because since this is negative 6 over 1 minus x to the 4th, if you stick a negative 1/2 in there, you get 3 halves. It makes the denominator larger than if I stick in 1/2. I stick in 1/2, the denominator is 1/2. So I'm going to get a bigger answer out of the x equals 1/2. Okay, so I need negative 6 over 1/2 to the 4th. Simplifying that, you get 96. And on the x to the 4th factor, doesn't make a difference if you put in a positive 1/2 or a negative 1/2. Either one is going to give you the same answer, which is 1/16. So, back over here, r sub 3 of x is going to be equal to 96, the maximum error on the derivative, over 4 factorial times 1/16, which gives you 0.25. So the error approximating p sub 3 of x, approximating by p sub 3 of x between negative 1/2 and 1/2 cannot exceed an error of 0.25 or 1/4. And that was part A. Part B, how many terms of the Taylor polynomial are needed to approximate the values for that same function with an error less than 10 to the negative 3 on the same interval? Okay. So we know that the derivative, maybe you didn't notice this, but if you keep looking at your derivatives there, the derivative is actually, it's always negative. It's n factorial on top over 1 minus x to the n plus 1 on the bottom. And that maximum error is always going to happen at x equals 1/2. And then the maximum magnitude is going to be either at the 1/2 or the negative 1/2. At x to the, we're trying to figure out what term we're on. So we're trying to find out r sub n of x needs to be less than or equal to n factorial, and I need to write this in here, I think, because you'll get lost. X to the n is going to be its biggest when you stick in 1/2, n plus 1 actually, and so this is going to turn out to be, I'm going to move down because it's not going to fit. So my n plus 1 derivative is negative n factorial over, and that actually you stick in your 1/2 and you get 1/2 to the n plus 1. And then over n plus 1 factorial. And then times by the biggest error, which is this guy right here. So that's 1 over 2 to the n plus 1. If we clean that up, okay, I'm going to move this guy up. That's 2, this guy right here. That's 2 to the negative 1, so it belongs upstairs. So it's negative n factorial, 2 to the n plus 1, over n plus 1 factorial, times 1 over 2 to the n plus 1. Oh, that's convenient. This cancels. And then this turns into n plus 1 times n factorial, so this cancels. So I get negative 1 over n plus 1. Now, to ensure that that error is less than, I'll write this out again. We know that this is less than or equal to 1 over n plus 1, and we want this to be less than 10 to the negative 3. If I solve this, this is going to be n plus 1 is greater than, I'm flipping the whole thing over, and so n has to be greater than 999. So if I have greater than 999 terms, the error is likely to be significantly less than 10 to the negative 3 if I'm near x equals 0. And this concludes 11.1.